All right, we got it. Oops. All right. There are 4 major risk factors for musculoskeletal disorders. Just briefly discuss each. That's not going to work. And these are broad categories rather than specific risk factors. And you'll notice that there is some material from the previous exam that's going to be part of the exams, but don't worry about studying anything beyond what we cover in the review from the old stuff. It's not on this study guide, but we will also cover the NIOSH lifting equation, just some basics from it. So what are the 4 major risk factors? These are broad categories. Yes. Good. Let me use my own here. Genetic. So someone else, not Calissa, talk to me about genetic. Just 1 or 2 sentences. How is that a risk factor for a musculoskeletal disorder? What if, using carpal tunnel as an example, what if anatomically your carpal tunnel just happens to be a little bit tighter than the average person's? Then there's going to be more chance for stuff to rub the median nerve, and if there's any inflammation at all in there, then you're going to get compression on your median nerve, and you're going to be more likely to have carpal tunnel. Yeah. So something that you're born with that you can't change. So it could be some difference in your anatomy, in your physiology, that is unfortunately puts you at a disadvantage. Now, compared to professional athletes, I guess most of us are at a disadvantage, but just compared to the average person. Were you gonna say? Okay. All right. So, yes, something anatomical or physiological that puts you, unfortunately, at a disadvantage. What was another one that Calissa had mentioned? Not Calissa. Okay. I'm going to say psychosocial because there are different things that go on in there. With psychosocial risk factors. So obviously the psycho part is the psychological part, but then there's also a social aspect to doing work. And we don't think about this often enough, I think. Maybe you guys do because of your degree program, but there are factors that are psychological and that are social that could increase the risk of you developing an MSD. Any thoughts on how either of those could do that? Let's say you have 2 groups of people. One group really loves their job and they have an awesome team with people that they get along with, but it's a high-risk job, let's say construction or something, for an MSD. And another group of construction workers that hate their job, and they hate everyone on their crew, and everyone hates everyone pretty much. Which one do you think might over time develop more MSDs? The second one, right? And why? And this one, I'm going to wait for you guys on this. Why do you think?
Actions that will cause injuries or like that.
Okay, so that psychological and social environment might change your behaviors and the way that you do things in a way that puts you at increased risk. I think you'll also, any little thing that happens, if you're in the second group, any little thing that happens is going to sort of, is going to be augmented in your brain. Like if you have a little bit of pain, it's going to seem way worse than it really is because you're just in such a negative environment. You hate it. And now you found another thing that you hate about your job because doing this certain activity causes you pain. Anyway, it would augment all those negative things. All right, another thing from Kalissa's list. Genetic, psychosocial. It's okay if you guys in the back row, just not Kalissa, if you answer. So there was a lecture dedicated to one of these. Biomechanical. And maybe that's one of the more obvious ones. This is the mechanics of the body, of biology. And we talked a little bit about fulcrums and levers. Depending on your anatomy, and that's something that's genetic, you may have an advantage or disadvantage for doing different types of work based on, say, where your bicep inserts onto your radius. If it inserts a little bit more distally, a little bit further down, you're going to have a greater mechanical advantage than someone else who's, say, inserts just a millimeter closer to the elbow. Because, so it's like, just like opening the door or trying to close the door, I guess we'll stick with opening. If you push on the door right by the hinge, you've got to exert a lot of force to get the door to just open. But if you're pushing further out, then it's easy. So the hinge in your arm is your elbow. And the closer you're doing work to the elbow, the harder it's going to be. But if your bicep inserts just a little bit further out, you have a biomechanical advantage. So the biomechanics has plays a big role in the formation of MSDs. And that's not just looking at genetics between people, but also just the biomechanics of a job. So it's not just looking at anatomy, but also the type of work that you're trying to do. If you're, and we talked about this, but if you're lifting a box and it's way out here, we did this with the NIOSH lifting equation. If it's way out here, when you talk about torques, that's increasing the distance, increasing the radius, the distance from the fulcrum, and it makes the torque go way up. And the last one. Okay. And in the NIOSH lifting equation, how is it that we capture information about the physiology of the task? So the biomechanical looks at the distances that you're lifting the box and the weight. Physiology looks at something else. It has to do with time. So the frequency and the duration. If you're, and really what it's looking at is muscle fatigue and physical fatigue over time. It's trying to prevent that. And if you think about it, not just for MSDs, but for injuries in general, if your job is to carry this box, on a certain path, and let's say there's this one spot where you kind of have to balance. Say there's like a gutter or something. I guess I'm trying to think of maybe a warehouse. There's this more narrow path where there's a small gutter, so it's not deep enough to require guardrail or anything, but you kind of have to keep your balance there before you continue on your path. At the beginning of the day, you're well rested, you have plenty of energy, you're going to be just fine. But at the end of the day, if you start to get tired, you're not going to be quite at the top of your game. And that's where you're at risk of maybe falling, or slipping, or straining yourself in a way that you wouldn't have at the beginning of the day because you were well rested. For number 2, I'd like you to be, what I'd like is for you to be able to dissect a few of the common terms for MSDs and be able to identify basically what kind of disorder we're talking about. So let's look at a few of them. There's one called epicondylitis. What does itis mean? Inflammation. Okay, good. So this is what I want you to do, is just be able to break down the name so that even if you've never heard of it before, you kind of have an idea of what is going on. Epi. So this one is a little bit harder. It's a word that means upon or on top of something. And a condyle, we didn't talk about this in depth. We just briefly mentioned it. Okay, good. It is, yes. So it's on both. So it tends to be on those hinge type joints. You're, whether this is your knee or your elbow, you have, I guess we'll say the elbow, but you have these protrusions. So these surfaces kind of that stick out on the side, and it's a spot for the muscle and the tendon to come in and attach. And so that's a condyle, is just I think it's spelled like that. It might be slightly different. If you misspell it, I'm not going to mark you off. But this is, there's a common term for this. It's called tennis elbow. So it's from lots of, if you think of a tennis player and the type of motions they're making with their elbow, it's from those types of motions. So not just tennis players get tennis elbow. What about tenosynovitis? So again, we have inflammation. What does this remind you of? Teno. So it's a soft tissue that we've talked about quite a bit. Huh? Tendon. Okay, good. So this is a tendon. So real quick with this one, it doesn't mention a tendon, but it is inflammation of the tendon that comes up onto the condyle. So here we have a tendon again, and we know, okay, there's going to be some inflammation involved. And we've got this synove. Has anyone heard of synovial fluid? So it's a fluid that tends to be in certain joints, not every joint, but certain joints, special ones, I guess, extra special, that need some extra cushion. So you have special joints. You know, I don't know exactly what type of joints tend to have it. I mean, I know, I think, for example, your knee and your elbow have synovial fluid, and there are others as well. I think, and I'm trying to remember specifically which body part tenosynovitis usually inflicts. I think it's actually in your hand. I'm gonna look that up real quick, but so you've got this. The synov from this word is not for the fluid from this condition, but there is also a sheath, a sort of, it's the fluid is in sort of this package, and it's the sheath that makes that package that gets inflamed and causes issues. Yeah. So there won't be terms that you haven't seen before. There won't be there won't be parts that you have not seen. And
Sorry, and that's the extent you want us to go to.
Yes, yep. So it is in the hand. Okay, de Quervains is also another term for this, but didn't really want symptoms. A tendon and its sheath. So that sheath is the synov part. It's a sheath next to a synovial packet, and I think it's sometimes called Mario thumb. Let's make sure on that. Oh, I think you're right. Mario thumb is something else. Trigger finger. So you're right. Yeah. See, I get some of the terms mixed up, but I think it's kind of funny that it's called Mario thumb. And I think that's from back in the day. I mean, my generation of video games when I was a kid, kids playing Mario too long. So carpal tunnel syndrome happens when you have inflammation inside and around the sheath in your wrist. So if this was, let's say, well, I guess it doesn't really matter, but you have some nerves coming in, and the nerve we're interested in is the median nerve. You also have a couple of your bones here, and then you have other little arteries and veins and tendons, lots of tendons and stuff coming in through. And I guess, so the sheath doesn't surround everything. That would be your skin, but you have a sheath that includes some of this stuff, and it protects it. And what happens is, for whatever reason, it will become irritated, or the tendons inside become irritated. They get inflamed, and when something inflames, it gets bigger. And so if any of this gets inflamed, it starts pushing on the median nerve, and it compresses it. So what happens to the nerve if you're getting permanent nerve damage? So there are two things. To be honest, I wasn't totally sure on this, and I was trying to find an exact answer, and I don't know, but I just know generally when you get this kind of a thing going on, you may get scarring, on the nerve and dead parts. So parts of the nerve may die. So it may scar and then die. You don't want that, obviously. So you're going to have either weakness, immobility, or loss of sensation if you have nerves dying. So you don't want that. That's what I'd be looking for there. You are the safety specialist at a plant, and a worker claims to have carpal tunnel syndrome because he has tingling in the anterior aspect of his left fifth digit, the little finger. So if you think of anatomical position, you're standing with your palms out. The anterior would be towards the front, right? Dorsal is back, anterior is forward or on the bottom. So on the anterior portion of his little finger. Do you believe him? So we didn't talk about exactly where the median nerve goes. There was an image, a figure, but it doesn't do a real good job of showing. The median nerve innervates your thumb, pointer finger, middle finger, and parts of your ring finger, but it does not innervate the little finger. So do you believe this guy then? No. Now, he may have something else, but it's not carpal tunnel, right? So that's one sign, one way to tell or differentiate carpal tunnel from something else is that that carpal tunnel will not involve the little finger, just, I mean, your larger fingers. What is the sliding filament theory of muscle contraction? I'm going to let someone else answer this one. Someone who is here to see the cheesy video on muscle physiology. You don't have to explain right now. Don't worry about using all the correct terms. It's just the concept of the sliding filament theory. On the exam, I'd like you to use the correct terms, but I wouldn't expect you to have it all memorized from just being in lecture. Okay, yeah, yes. And he made an analogy with a basic activity. Okay, good. Yes, so it's like pulling a rope, hand over hand, basically. So that's the concept, the basic concept. But I'd like you to be able to use the specific terms when you answer that one. So, and you could just describe the basic process. So calcium comes in to that part of the muscle, binds to troponin and tropomyosin. So it's all in the lecture from last time. You can look at that to get the details. So we're just going to cover it real quickly. Calcium comes in, from I like his video because he's funny. He said the troponin and tropomyosin are bought off with, they're like bodyguards, and they got bought off with calcium. And he says, I paused it right during this joke, and I didn't mean to, but he said, I prefer cash and nachos. But anyway, if he was going to get bought off, then, I don't know his name, but you can buy him off with cash and nachos. But anyway, so the troponin, tropomyosin get calcium, they're bought off, so they leave. And so the myosin is then able to bind with the actin. The actin is kind of like the rope, and the myosin is kind of like the hand. It binds and pulls and uses energy in that process. And that's how you get muscle contraction, is that happening over and over in lots of little places. Calissa? Yeah. Yeah. Let me, I'm going to look for it real quick right now and just leave it up so I know and remember to do that.
When will this test be?
It's the Tuesday after spring break. Okay, so if you go to YouTube and you type muscle physiology, it's the first one. It is by, it's called Crash Course. And yeah, I guess, I don't know that guy's name, but I guess his name is Hank. Anyway, it's from Crash Course, and it's part 1 on muscles. I'm going to leave it up, though, so I remember. I did not ask you to do this on the last exam, but I think it's a fair question. It's something that you've done already. This will just be remembering how to do it. Given these data, find the reactive force and the moment at the elbow. So if you imagine an elbow, so we're just going to have 2 answers here. One is going to be force, and the other is going to be torque. For the force, you just add these 2 numbers together. So for force, remember, we just add up the forces together, and we get the force. So in this case, it would be 115.1 is our force at the elbow. For the torque, it's a little bit trickier. So you would need to use a calculator. Please bring a calculator. And if you don't have one, I have a couple you can use. We also have, so we have an angle theta. We have 2 distances here that we need to keep in mind. And does anyone remember the equation for torque? So there are 3 parts to it. We're going to use each part from here. So force multiplied by the, I say R, the radius, but it's the distance. So it'd be these 2 values. Multiplied by the sine of theta. So that's all you would need to remember for that. Once you get the torques, then you'd add them up. Let's do it real quick. We got to make sure we match the right things with the right parts. We have the forearm. We have the center of mass of the forearm and the load. This would be the elbow. Oops. Theta is not that way. All right. So we have the length of the forearm. So L1 is going to be this whole thing right here. We have the distance from the elbow to the center of mass. This is going to be that lambda 1. Just know that's what that is referring to. So let's call this elbow and arm. Or, well, I'm trying to think what would be the least confusing. Let's do them one at a time. Maybe that'll be the most straightforward way to do this. So let's just look at let's first just find the torque for the forearm. So this is the center of mass for the forearm. That's the distance we need to use. That's going to go here. We're going to use the same theta for both. It's 30 degrees. And we need to find the weight of the forearm. And that's this top one, 15.1. So we have 15.1 times our distance, which is, we need to do in meters, remember? And 29.1 centimeters is the same thing as 0.291 meters. If you just move the decimal 2 spots, then you've got it. So I moved my decimal 2 spots. So that's newtons, meters, and then we've got the sine of 30. So that's what we would punch into our calculator, and that would be the answer for that torque. The other torque would be then the same idea, just the other numbers for the load. So we've got 100 newtons times the other distance, which I'm going to convert it to meters, 0.427 times the sine of 30. And then we'd add these two values up. Let's just do it real quick so that it's not what I meant. So every calculator is different. And I'm just now learning the sine of 30 is 0.5, so that makes that easy. So 0.5 times 0.291 times 15.1. And if you remember from the assignment that you did, generally the torque is less than the force. 2.19, we could really round that to 2.2 for the forearm. 2.2, this would be Newton meters. And for the second one, we got 0.5 times 0.427 times 100, 21.4 Newton meters. Questions on that? Yeah, yep. So we would add those two up to get our final torque at the elbow, and that would be 23.6. What are some of the factors that contribute to human variability? We looked at a bunch of graphs for these, and you don't really need to discuss it in any more, well, I'll leave this up for a minute, in any more depth than what we talked about in class. Just what are some of the categories that make us different in terms? So human variability, think of anthropometry, just our measurements, and why might my femur be shorter than someone else's, or my arm span longer than somebody else's. Okay, so yeah, yes. So genetics, what generally, how do we have different genetics across the population? What are some things? Okay, so ethnicity and race both will have some influence on that variation. So you'll find that if you look at the charts, I think, if I remember right, those who are African or descended from Africa, their torso to leg ratio tends to be, or let me say this the other way, their leg to torso ratio tends to be larger than those from Asia, for example. And I have no idea why that is, but that's how you would interpret that graph. So those from Africa, their legs compared to their upper body tend to be longer than people from Asia. Any other ways? Okay, gender, good. And there were some graphs on that as well that we looked through. So be ready to just name a few of those things. I mean, it's not a really long list. And then just give an example. One example is fine on how some of these factors influence human variability in terms of body measurements. So now I'm going to erase this if that's okay. I should have asked before jumping in and doing it, but okay. So what is a normal distribution? I mean, it looks like that, kind of. It's not a perfect drawing, but so for this, if not obviously not all of these are on the exam. If this is on the exam, I would like you to draw a normal distribution. It helps for me to know that you know what it looks like, as well as to being able to describe it with words. Okay, so yeah, you're on the right track. A normal distribution is, it looks like a bell. That's why it's called a bell curve. It's sometimes referred to that. Human, so anthropometry looks like this. So when you measure the human population in terms of measurements and dimensions, it will look like this, which is nice because in my field, it doesn't usually look like, it's not nice and neat like this. It's usually a log normal distribution. That's beyond our scope. But when you have a normal distribution, then the ways that you measure central tendency, or where the middle of the group is, will all be in the same spot. So if I draw a line right here, then the mean, which is the average, the median, which is literally the middle, so the 50th percentile. If I just lined up all the numbers on the board, and I just went, if there are 100 numbers, and I counted to 50 and drew a line, then that would be the median. So the median literally means the middle. The mean, the median, and the mode, interestingly, which is another way of measuring the middle, although we don't use it a lot, but they would all be in the same place. And what a normal distribution allows us to do is make certain assumptions. And this is getting at your point that we can so I'm going to step back just a little bit. No one has enough money or time to measure every human on the planet, or even in our country, for example. Like, we don't have enough time or money, so we don't measure every single one. We take a sample of the population and say we measure 100 or 1,000 people. If we find that the data for that are normally distributed, which we would expect to find, then we can make certain assumptions about the population in general. And it allows us to divide this distribution into standard deviations. And I'm trying to remember these smaller categories. I think each of 34%. Someone could look this up. If someone could look this up and correct me if I'm wrong, that would be great. But 34% of the population is found on either side of the average in that first standard deviation. So if you looked at both, plus or minus, rather than either side, then about 68% of the population is found in that first, on either side, one standard deviation away from the average. And remember, standard deviation is simply a way of knowing how spread out our data are, or how variable our data are. So if we have, if we had a distribution that looked like that versus this, well, then we know this one isn't very spread out. And so it would have a really small standard deviation. This top one would be very spread out, and it would have a large standard deviation. If we go one more standard deviation, let me try and do that math real quick. So I know the total is going to be 95%. About, but I'm trying to remember what each of these individually is. So we'll round it to 14. So it's not exactly 14. I'm rounding, but about 14% on each of these. So that second standard deviation away on either side is 14. If you add all of it up, then you're going to get it about 95%. And so to your point, if human dimensions are distributed normally, then we can assume if we have some data and we know where the average, the middle is, we could use our standard deviations to estimate the dimensions at these points right here. So let's just say it's heights. You have a workstation that you're designing for somebody, and maybe you're not going to be able to fit Shaquille O'Neal, and you're not going to be able to fit, the 4 foot nothing person like Lori from the city of Prescott. I don't know exactly how tall she is, but she's pretty short. She's over here somewhere. She might be in the 95th. I mean, within that 95%. I'm not sure. If you think about it, so right here we've just got 2.5% of the population and just 2.5%. So most NBA players are probably in here. Shaquille O'Neal is in there. I use Shaquille O'Neal because he was prominent when I was was younger and followed basketball more. Who's really tall now and like a dominant center in the NBA? Is there anybody? It seems to have moved. There's sort of like eras in the NBA. Sorry, I'm getting on a tangent, but like eras where different positions seem to dominate the game. Now, I don't know if it was because of the players themselves. So you had like Magic Johnson and Michael Jordan. I'm not familiar with older than that, but so they were shooting guards, and actually Magic Johnson might have been a point guard. So I might be lying. But anyway, shooting guards seemed to dominate the game for a while. And then Michael Jordan retired and Shaquille O'Neal came along. Maybe it's just these individuals are just so dominant that they kind of change the game. But Shaquille O'Neal came along and he was tall. When he was young, he wasn't like solid, but it didn't take him long in the NBA to get solid. So he was like, I don't know, 350 pounds of muscle. And and he was like 7'2". So it wasn't, you couldn't just drive the lane and dunk on him or something. Anyway, he kind of dominated, and the Lakers won a bunch of championships, which I was bitter about, but because I've always been a Suns fan, and they tended to beat us in the playoffs. But and now you have forwards like LeBron James, although there's sort of like this, I don't know, because there's like Steve Curry is rising as well. Anyway, enough of my tangent. Those players are mostly up here. Not all of them. There are some short NBA players, but if we want to design a workstation and we decide, okay, we don't have Shaquille O'Neal here, we don't have any pilots that are Shaquille O'Neal, and we don't have any pilots that are 4 foot nothing. We then design our workstation for this group here to make sure that now this is something related to chairs as well. Do you make a workstation, if you're designing it, that is just, you make it and it's a single height and it's done, or do you make it adjustable? What do you do? Huh? Adjustable. So you can't, maybe you'll have different workstations that are like, they're not adjustable, but they're at different heights or something. That would be an option, but I think the better option is to make them adjustable. And you don't necessarily have to make them adjustable to accommodate Shaq, but make them adjustable to accommodate up to whatever this line is. And we're gonna do some of that in just a minute. That's how it's applied, though, is it allows us to make certain assumptions about our population and helps us estimate what the upper and lower bounds would be for body dimensions, for example, so we can design our workstation better. Don't worry about number 9. We didn't really talk about it, and I'm not too concerned about it. I think of that more for like heat stress than for ergonomics. And what is the principle of the limiting user? We just barely touched on this. It's the idea. So the limiting user is the person that will constrain your design of the workplace the most. So if you, let's say you are designing cockpits and you happen to have a pilot in your airline that is the same as Shaquille O'Neal. I mean, it's not Shaquille O'Neal, but same body build. That person is going to be your limiting user because they're going to constrain your options for designing the workplace. So you're going to have to make quite a bit of accommodation for that person compared to the average person. So they generally tend to be on the high or low end of this spectrum. So that the official definition there is the person that constrains your design, the user that constrains your design the most because of whatever it happens to be. We're talking about body size and dimensions, but it could be something else. What do you want for an ergonomic chair? What would be defined as an ergonomic chair? Okay, adjustable. What should be adjustable? Okay, so you want armrests, and we're going to get a little specific here, but you want armrests that both go up and down and also side to side. So you may, and there are ones that even they'll move forward and backward. So it would be nice to be able to adjust those armrests in 3 planes of movement: up and down, left and right, forward and reverse. For the the back, you had mentioned, what do you want to be adjustable there? Or how do you want it to be adjustable, I guess? Okay, so you want to be able to adjust the recline, the angle, also the tension of the recline. So has anyone ever been kind of reclining in a chair and someone comes behind and like pushes down on it, or like that happens to me all the time at home with our office. Like we have a little computer chair that we use at our computer in the main living room, and my kids will run up and they'll jump on the back of the chair while I'm sitting on it. So I'm like, you know, I'm afraid I'm gonna like hit the floor anyway. But you want to be able to adjust that. Some people like to be able to just really lean back in the chair without much tension there, and some people like more support, more there. I haven't had the chance to be in a chair that does this, except in newer vehicles, but a chair where you can adjust the lumbar support. That would be nice, right? So the height of the chair, you want to be able to go up and down to different levels, and also the seat pan, you want to be able to adjust the angle of that as well. I think that's it. The slides have all of those. I mean, they address the things that you should be able to adjust, but not necessarily the ways that I just described. I think that's it. So that would be an ergonomic chair. Something that could do all of that would be awesome. Okay, so here's where we didn't use this equation in lecture. It's not that difficult. Just once you know what goes where, you can plug and play, basically. I'm going to move over there. So this is where the application comes of a normal distribution. We get to make certain assumptions, and it's nice to be able to do that. So let's say a population has a mean arm length of 28 centimeters. Let's say you went out and you measured, I guess, well, if you were say like a certified professional ergonomist, it might be your job to do this sort of a thing. So you go out and you measure the arm length of everyone at your site, at your operation, your facility, whatever, airport, airline, and you find that the average arm length is 28 centimeters. So arm length, the average is 28 centimeters. And the standard deviation is 8 centimeters. Excuse me. Well, I think I've used the symbol that's for a sample, not a population. They change based on what we're talking about, and this is a population. What is the 95th percentile value? So what is that interval? And if you look at this equation, you see it has plus and minus. When I say what is the 95th percentile value, what I'm wondering is, what are these two numbers here? There and there. Well, that's wrong. This would actually be, we're looking for the 95%. let me erase this. We're wondering about this 95% of our population. Technically, though, the percentiles will be 97.5 and 2.5. Those would be the percentiles, but the in between these two numbers is 95% of our population. So that's what this question is asking is, and if we're talking about arm lengths, what are the lengths that are at the 97.5 and the 2.5? Let's just draw this quick. So we want to know what that is and what that number is. We know that right here is 28 centimeters. And that one standard deviation is 8 centimeters. So we want to know where to go to get those. Oops. So we use this equation, and it is our mean plus or minus standard deviation multiplied by this z-score. I will provide the z-score. You don't need to look it up in a table or anything. And in this case, for this question, it's 1.645. So what we do is we look at 28 plus or minus 8 times 1.645. And if we do that, so we get 41. 41. Sorry, I'm writing sideways. We'll round up 41.2. And 14.8. That's a good question. That's a good question. For a sample, now we're using a population, but for a sample, I would imagine that, well, why I'm like noticing all these staples on the ground now, but we don't have measurements for every single person in the population, and so we have to, when we make that estimation, we want to have a certain amount of confidence in our estimation. With a population, and so that's what I'm not sure on. So I'll have to get back to you on that. I'm not sure. Yes. Yes. So last two things, they're from the last study questions. Let's see. Okay, I do have that, so I don't need to worry about OneDrive. '18 and 19 here. Can't really scroll down anymore, but So down here at the bottom, see, I can go a little bit. Discuss the interpretation of the lifting index of the NIOSH lifting equation. Let's say that you do the equation, you get and you get a lifting index. I mean, you won't have to calculate it on the exam, but I would provide you a number. Let's say you get 2.3. What does that number mean? If your lifting index is 2.3. Okay, so you're over the recommended weight limit and you should fix the design. How much are you over the recommended weight limit? So you're 2.3 times over what the recommended weight should be. So let's say an easy one for this would be you did the calculation and the recommended weight limit was, well, your recommended weight limit was 10 and the actual load in your lift is 23. So that would give you a lifting index of 2.3. Your load is 2.3 times higher than what it should be according to the NIOSH lifting equation. So that's how you'd interpret that number. One is it is too high. It's over the recommended weight limit by 2.3 times. Does that make sense? So it's 2.3 times too heavy for to do that task and to do it safely, without increasing your risk of an MSD, specifically for the lower back. What if the lifting index is 0.75? You're good. So if you want, you could also like multiply this number by 100, and that would be the percent compared to the recommended weight. So in this case, our load is 75% of the recommended weight limit, meaning we're under it and we're good. If you hit 100% or if you go over 1, that's when it's not good anymore, right? So be able to just discuss that briefly if I give you a number for the lifting index, and discuss the applications and limitations of the NIOSH lifting equation. So what kind of lift is it for? Okay, so it can be used for a lift that's done repeatedly. Is it for if this was my load, is it for this kind of a lift? Why not? Okay, good. So it's above my shoulders. So it should not be above the shoulders. Let's go ahead and go to the other limitations. There are several. Oops. Okay. And I don't remember them all. Another issue with that lift I just did is that it was with one hand. So it's a two-handed lift. If it's over 8 hours, does not apply. So if you remember on the calculator for the frequency and the duration, there's not an option to select over 8 hours. So it can't be over 8 hours. It's for standing. So it's not for any task that you're doing while seated or kneeling. It's not for a task in a restricted or confined workspace, not with unstable objects. It's not for doing any carrying, pushing, or pulling, lifting with wheelbarrows, high-speed motions, or on a slippery surface is what that is. Sole to floor coefficient of friction. I'm assuming that's how slippery the surface is. So if you're working on really slick surfaces, then it does not apply. Has anyone ever spilled like if you had saltine crackers or something real fine and you spill it on the floor? No. I'm thinking of saltines, but the example, well, two examples, one from industry and one I guess is from industry, but when I was an undergraduate, I had a job working in a molecular biology lab, and we were supposed to make this agar with it's a powder and water you mix together and it makes a gel. And the powder was really fine. And if you ever accidentally spilled some, so sometimes right where the agar was in the lab people had spilled, never me, right? Maybe sometimes I spilled, but people would sometimes spill and it would be right there. It was super slick with just that little bit of powder down there. And I'm thinking of the mining industry. They process, there's an ore called molybdenum. They call it moly. After they process it and it comes out at the end as a concentrate. It's like this really fine powder, and it gets on the floor everywhere in the facility. And that is pretty slick as well. But anyway, it does not apply to slick surfaces. Any questions? Any other questions? So Calissa, I'll get back to you on yours about using the z-score instead of just adding and subtracting your standard deviations. I'm not sure on that, but all right. Thanks, guys. Be safe over spring break. Also have fun. That's important.